Now let's consider one more relabeling. Things are getting kind of cluttered here, but we're going to do one more relabeling. What if one cycle takes 20 seconds? Now we've labeled the graph, we've labeled the horizontal scale in cycles, t in cycles. We've labeled t in arc distance, assuming a equals 1. Okay, we've labeled at least this one in degrees. Okay, there are many ways we can label this axis depending on what it is we're modeling. What if this is, let's say, a blade of a windmill that takes 20 seconds to complete a cycle? Well, we see that there are about 20 marks. 20 marks actually ends up here a little shy of this point, but let's just round that off and say that 20 seconds to do the whole thing. And I'm going to relabel this graph approximately with that idea, with the idea that it takes 20 seconds to complete the cycle. Well, in that case, I would have t in seconds, and this coordinate here would be approximately 20. This one at the halfway would be approximately 10. Here at the maximum point be approximately 5. And at the 3/4 point it would be approximately 15. And now we have a model of the motion of a windmill with amplitude A, say the radius of the circle, big windmill, let's say radius is 100 feet. Okay, so if A was 100, we could label this as 100, label this as negative 100. I don't have room to label it, but having the 100 here implicitly makes this negative 100. We can see where the windmill is, or where the tip of the blade of the windmill is, vertically, how far above the ground, or at least how far above the center of the circle, or in the case of negative values below, as a function of time. How high is the blade of the windmill as a function of time? Down here, we could have the model showing us how far to the right or left of the center point that blade is as a function of time, the tip of the blade. Okay, so that's another possible model. We might not be all that interested in just where the tip of the blade is at a given time. Mostly what we're interested in is how fast the thing is rotating, but we could model that, and there are many cases where we would want to model that. In fact, this would be a model of simple harmonic motion. Okay, so if we had a weight on a spring going up and down, this with an amplitude of 100 something probably wouldn't be 100 feet. That'd be an awfully long spring. And this could model the motion of that weight as it goes up and down on a spring, and in ways that we'll see much later in our course. As a specific interpretation of this graph, let's assume that we do have this windmill with, say, 100-foot blades, and you're down here in the ground, hopefully well below the point where the blade hits its lowest position. If it's a 100-foot blade, let's put it in a 200-foot tower. So that at the top it would be 300 feet off the ground, at the bottom 100 feet off the ground. Now let's just say that you happen to be under the blade at the moment it reaches this position, rotating in this direction. Then as the blade rotates, if you want to stay under it, you're going to have to start moving to the left. You're not going to have to move very fast at the beginning, but by the time you get over here, you're going to have to be moving pretty doggone fast. And then, of course, you got some speed built up, but now you're going to get to slow down a little bit to where you momentarily come to a stop here. And if you want to stay directly under the blade, you then keep accelerating this way, then slow down as you move toward this point. Okay, so you try to run exactly under the tip of the blade. Imagine the sun is directly overhead. You're somewhere in the tropics at the right day of the year. and you want to keep the shadow of the tip of the blade right on the top of your head. Don't know why you would want to do that. There are easier ways to stay cool. But let's say you did. Okay, just an image to carry along with this model. Then what does this graph tell you? Well, you see I've relabeled. I got T seconds in yellow, so I've got my yellow labeling here. And remember, these are approximate. It takes just a little more than 20 of these marks to get around, but we're going to ignore that. What information do you get from this graph concerning maybe how fast you've got to move? What aspect of this graph tells you how fast you want to move? Remember, Y is your position on the ground, and T is now your time in seconds, and your position is measured in feet. Okay, well, a rise of this graph, a rise between 2 points of this graph, is going to represent a change in your position. Okay, so for example, the rise between this point and this point is negative 100 feet. Okay, 100 feet in this direction. The run is 5 seconds. 100 feet divided by 5 seconds is 20 feet per second. So an average speed from here to here would be 20 feet per second. Can you run that fast? Well, most people of college age can run that fast. I could probably run that fast for a very short distance, except I'd be risking injury, so I'm not going to even try. Okay, in any case, that's pretty fast. You know, that's the pace of a 4.5 minute mile. Obviously, very few people can keep that up for a mile, but most people can run that fast for at least a little ways. Now, that's the average speed you would need to run from here to here before the blade got to this point. However, you got to speed up to get from here to here, so you start slower than you end up. And the question then is, how fast do you have to be running at this point? Well, we could approximate that. We could approximate where you are here, maybe 30 feet from the center point, and 1 second from the center point, so maybe you have to run at 30 feet per second. And 30 feet per second is pushing it. That's around 20 miles an hour. Most people can't run 20 miles an hour. Fastest any human has ever run, at least been measured accurately, has not exceeded 28 miles an hour, and most of the world's fastest runners have been clocked in the last 50 years with that kind of accuracy. 27 miles an hour was achieved in the 60s, and 28 miles an hour has not yet been achieved. So that's really moving. Chances are, if that's an accurate estimate, you're not going to be able to run fast enough. An even more accurate estimate, if our graph is really good, could be obtained by just doing a tangent line, a line that runs parallel to the graph right at the center. And I'm going to actually sketch that off camera. Now, we don't have a completely accurate graph here, but if I sketch the tangent line from here to here and then project this down, we see that this point projects down to about the 2 second mark, which is about 3 seconds from this mark, so that the magnitude of our slope, of course our slope is going to be negative, but we're just interested in how fast we're going, so we don't worry for this question about positive or negative. It looks like we take not more than 3 seconds to go the 100 feet, which indicates something over 33 feet per second. So it's even a little faster. And if we look at how the tangent line goes on this side, we estimate closer to 50 feet per second. Tangent lines here estimate still around 35 feet per second, 30 to 35 feet per second. Now, what I've got here is a stick figure representing you. You're not really running up here inside the arc of the blade. You're down here in the ground, but I couldn't draw you down here reasonably. Also, looks like you're about 50 feet tall, and I don't think you're that tall. So this is just a schematic indicating the fact that we're talking about somebody running from here over to here and staying directly under the tip of the blade. That person, and nobody can actually do that, I don't think. For this blade, I think your maximum speed would exceed what Well, no, maybe there are people who can do that. Most of us can't. Okay, so this person is in simple harmonic motion, what we call simple harmonic motion, something that's a very important type of motion. It's very universal, very important for engineering and many other types of applications, and of course physics. So this person would be in what we call simple harmonic motion. Simple harmonic motion simply meaning that you follow a point moving around this circle, either along the x-axis or the y-axis, or in fact any straight line through the origin, in a way that we'll talk about later. But that's one reason this circular model is so important. Now, just a quick little blurb. I couldn't resist doing the actual analysis. The model here would be 100 times the cosine of pi over 10 t, because pi over 10 is the number of radians you're going through per second if you move around the circle in 20 seconds, as you can easily verify if you think about what I just said. The derivative of this function, and we have to have angles in radians if we're going to do a derivative, is by the chain rule, negative 10 pi times the sine of pi over 10 t. Now it's 100 feet, so that's 10 feet times pi. The maximum value of y prime occurs when the magnitude of the sine is 1, and that gives you 10 pi, and that's going to be 31.4 feet per second. So the estimates we get from the graph and from other basic estimates are pretty well consistent with this. We estimated usually between 30 and 35 feet per second. And that's consistent with our 31.4.